Okay, so now let's prove this this periodic property of the Fourier transform in a special case. And the special case that we'll look at involves, let's assume that that the period R divides n, and let's assume that our initial superposition is non-zero only on multiples of R. So let's say that our initial superposition is of the form sum over j of j times R. So these are the only values which have non-zero amplitude. And in fact, how many of them are there going to be? Well, you know, since R goes into n over R times, so we'll have j equal to 0 to n over R minus 1. Right? So there'll be exactly n over R such values. And each should have, you know, since we want them to have equal amplitudes, each will have amplitude square root R over n. So this is our initial superposition. It's non-zero only for these multiples of R, and it has amplitude exactly this much at each one of them. So now we want to understand what happens when we apply the Fourier transform to this. And the claim is we get a similar superposition with period n over R. So in other words, we get k equal to 0 to something, and we'll get non-zero amplitudes only at multiples of n over R. So it'll be k times n over R. So n over R, 2n over R, and so on up to R times R minus 1 times n over R. So there'll be exactly R such non-zero values. And so each should have amplitude 1 over square root of R. And k goes from 0 to what? Well, you know, there are R of them, so you'll go to R minus 1. Okay, so how do we prove this? Well, to prove this, we have to remember what our Fourier transform is. So remember what our Fourier transform, what f sub n looks like is, well, it's 1 over square root n times this n by n matrix. And what's the n by n matrix? Well, if you look at the x, yth entry, it's omega to the xy. Okay, so what is this telling us? Well, it's telling us if we want to know how much this particular entry gets mapped to that one, well, how much does this entry get mapped, you know, what does it contribute? So okay, what are we trying to do? We are trying to figure out what is, you know, if this was, if the amplitude of this entry was beta, what's beta, right? Well, okay, so the amplitude here will get some contribution from every non-zero term here. What contribution does it get? Well, it gets omega to the power of j times R, which is in this case y, times omega to the x, which is times k times n over R. Okay, so that's this omega to the this, times the amplitude you started with, which is square root R over n, and then times 1 over square root n. And now we must sum this for all j going from 0 to n over R minus 1. So that should be the amplitude of this particular entry. Okay, so what is this value? Well, you get this is equal to square root of R over n summation j equal to 0 to n over R minus 1 of omega to the power of, these r's will cancel, and it's j times k times n. But remember, omega to the n is 1. So this is just 1. Right? So you'd get square root r over n times 1 added n over r times. So times n over r, which is exactly 1 over square root r. Okay, so what we've proved is that for each multiple of n over r, the amplitude is exactly 1 over square root r. Now, there are exactly r of these values, right? And so the amplitude is exactly 1 over square root r for these r values. What's the amplitude at these other points? Well, remember, this is a unit vector. And we already have a unit vector. This output vector has to be a unit vector. We've already accounted for a unit norm in its amplitudes at 0, n over r, 2n over r, and so on. And so the amplitude at every other point has got to be 0. Okay, that's one way of arguing it. The other way you can argue it is if you instead of looking at a point of this kind, a multiple of n over r, you just look at the amplitude of some other point which is not a multiple of n over r. And then what you'll see here is that these omega to these powers, these will just precess around and they'll cancel out in the way we saw before. Okay, so in either case, what we've shown is that if you start with this periodic superposition with period r, you end up with this periodic superposition with period n over r. Okay, so now we are ready to look at our primitive, which is period finding. This is what we are going to use in Shor's algorithm for factoring. So this is sort of the last thing we are going to do in this particular video. So let's try to understand how period finding works. So now, suppose we are given some function f such that the set 0 through n minus 1 is mapped to some set S. We don't care what S is. But we are told that f is periodic with period r, so some period r which divides n. Okay, meaning f of x equal to f of x plus r, let's say mod n. So we're working modulo n. Okay, so we are wrapping around it. Moreover, so we are told that f is periodic, but within each fundamental period we are told it's 1 to 1. So f of 0 is different from f of 1, is different from f of 2, is different from f of r minus 1. But then once you get past r minus 1, you keep repeating. So if you were to plot out, if this was x, that was f of x, then maybe this is what f looks like. It's 1 to 1 up through, let's say that's r minus 1, that's 0, and then starting from r you have exactly the same shape, and then starting from 2r you have exactly the same shape, and so on. Okay, so that's our function f. And the way this function is specified to you is by a black box or some program to compute f. So you're given a black box or a circuit, C sub f. And what you want to do is you want to determine the period r. Okay, so now in general, n is going to be very large, and so is r. And so what's not a very effective strategy is to just take your circuit for computing f and feed in random values for x, hoping to see a collision. So this is not going to be a very quick way of computing r, because you'd have to do work proportional to r or square root of r, something like that.